No, yes.
Really? It's so good. Hope your night's all going well. You guys have a little bit longer if you want to grab food and anything. We're CAIS++'s e-board. If you're not familiar with CAIS++, we're the Center for AI Society undergraduate grant, and we participate. There we go. And we participate in AI research throughout the semester. We also host a curriculum every semester. Thank you all so much for being here. This is a quick outline of what we're going to be doing tonight. So, a quick introduction, welcome, and then a few of our project teams, and then our curriculum presentations, followed by some ending remarks. And just to introduce us as the team up here that runs things, I'm Shannon. I'm one of your co-presidents this year.
I'm Nico, also co-president.
I'm Shantanu. I'm the VP of Fellowship.
I'm Natalie. I'm VP of Curriculum.
I'm Sam, VP of Projects.
Boo! Yeah.
All right. I want to thank our sponsors, Apple, Boeing, Chevron, for helping us throughout the semester, and also Victor Dukina, our advisor, director of education.
In addition to our project presentations tonight, our fall cohort this year has spent their semester in our curriculum program, and as a little capstone, we've had them put on prepare presentations. Also present to you tonight, we have given them an option of either presenting on a ML paper or finding a data set and building a model and working with that data to kind of what they've learned over the semester. So we will try and release those presentations, post the project presentations. I'm really excited for you to see what they've been up to recently. Sam? So we had two main projects running this semester that we'll be presenting on. So VP of Projects forgot about. So those two are our more long-term, most likely going to be 6 months to a year long of research, which are groups of about 4 to 6 people. So those presentations are a little bit longer and a little bit more in depth, just to give you guys a heads up. Without further ado, let's get this presentation started.
All right, so welcome. This is our team, Ocean Pollution. I'm Ocean, this guy's Pollution. I'm joking. Beautiful man. Sam, I'm Rob, I'm the co-lead.
I'm Sam, I'm another co-lead, and
I'm Ishu.
so he's our one project member that can make it today. If you look on the slide, there's a couple more names. Priscilla, Anthony, and Fiona couldn't make it today, unfortunately, but we really appreciate their contributions. Yeah.
First, the problem. It's a big problem right now, you know? There's a lot of plastic going around in the ocean. And the majority of it comes from developed nations, donating it to foreign nations and pay them to take it. Then developing nations don't know what to do with it. They kind of just like, all right, straight to the ocean you go, and then all the turtles die, you know? It's kind of bad. So the ocean currents take that plastic, spread it everywhere, unpredictable places, and even like, you know, endangered animals and species natural habitats. That's horrible. So we come up with a solution, or the professor who are working with solution. Developed nations are going to figure out the optimal amount of plastic to keep in-house for processing and recycling, as well as where and how much to send away. Therefore, we need to study the ocean currents of X to understand the optimal locations and amounts to send.
Okay, so for our project, we use a subset of machine learning called reinforcement learning. And it's basically like learning from rewards. How it works is that you have a goal, like it's usually for game environments, and you have like a goal where you're trying to maximize the potential reward possible. And to do that, you'll be given actions that you need to do along the way. So you have like an agent, and like, you know, for example's sake, let's say like you're controlling Pac-Man. So like Pac-Man's the agent in this case. And then it interacts with his environment, which is like your typical 2D environment. And over time, it's going to be making decisions as to where it wants to go. Maybe it wants to go right or left, and then this is referred to as an action. And each time it moves, it goes to a new state, which is like maybe its location. And depending on the location, the new state it goes to, that generates some type of reward, or it could also be a punishment if that was the wrong action to take. And the goal is like through a sequential linear of steps, you have to try to maximize the reward as much as possible.
Okay. So the objective of reinforcement learning is to learn a policy, an optimal policy, so that the agent can know which actions to take in a given state. And how does an agent learn this? Well, we use something called the Bellman optimality equation. So let's break down this equation on the slide. First, let's look at the right-hand side of the equation. You see Q star S comma A. This function is called the optimal state action value function. And what essentially it returns is, given some policy I, a state S and an action A, return the maximum expected reward from taking action A in state S and then afterwards continuing to follow policy I. And that's essentially what it's doing. And that function needs to satisfy the other side of the equation. And let's break that down a little bit. So on the left side of the equation, we have the expected value or the expected reward from taking action A in state S. That's represented by R sub t plus 1. And then that like jumble of equation on the very right-hand side is the maximum expected discounted reward that is achievable from any possible next action state value pair. And what this essentially means is just the reward essentially from taking action A, and then the expected maximum reward from solving the rest of the problem in all subsequent states. So why is this important? Well, I mentioned earlier, we were trying to learn a policy, right? And essentially, if we are able to figure out this function Q star S comma A, if we are able to figure out what it is, we essentially have learned our policy. And what do I mean by this? Well, if we have an accurate Bellman optimality equation, or accurate optimal Q function, essentially all the agent has to do is look at the state it's in, plug in all the possible actions that it can take in that state, and just find the maximum, because this returns the maximum expected reward from taking any action in the state. So that's basically how the policy is learned. I should also mention that the value that this function returns is called the Q value. Q just stands for quality, essentially.
All right, guys, don't worry, you don't get anything out of it. That's like the whole lecture put into like 2 minutes. You're gonna learn 360 eventually, and you're still not gonna get it. Don't worry about it.
Yeah.
On to the next.
There might be some technical inaccuracies in what I'm saying. Just forgive me, and you can correct me during questions or ask any questions if you don't understand it. So before we dive into deep Q learning, which is what we use, let's look at some more traditional method of Q learning. This is something called traditional or tabular Q learning. And essentially, the objective of Q learning is to find the optimal Q values for each state action pair. And tabular means table, so you can see there's some tables up there. Horizontally, on the top, there's a list of all the actions you can take in this environment. And vertically is a list of all the different states that you can visit in this environment. And you can see where those two rows and columns intersect. Like for example, right here, this is the Q value for taking the action up in state 8. So I hope that makes sense. And the objective is to, you notice on the very right table, they are all initialized to 0, because when we're first exploring the environment, we have no idea what the optimal Q values are, right? So the idea is to use a process called value iteration, or through a combination of exploring the environment or exploring the environment and the actions in an environment, we can use the Bellman optimality equation to converge on the optimal Q function, Q value function. That might not make a lot of sense. If it doesn't, don't worry about it. But that's basically what basic Q learning is. Next slide.
Okay, so in order to better understand how we could use like Q learning and different types of models for our particular case, we found this one paper that basically took in a different type of approach. So in typical reinforcement learning applications, as you're exploring like different states and like taking different actions, there's usually like a delay between your actions and rewards. And for our case, if we, for like a game environment, that can sometimes not be ideal because your reinforcement learning has a lot of correlated states together and you want to be able to figure out a solution as quick as possible. So in order to integrate that, we use the Atari paper talks about using something called a deep Q network, which we'll talk about more, and integrating it with a CNN. So you can get better optimal scores. And how it works is that the input data is like the raw visuals, like the raw pixels from like your 2D environment. And then the output value is like the function that tells you the maximum reward, the future rewards that you can get given a state or action. And then the Atari paper discussed that using the model that they built, they actually were able to outperform like on 6 different Atari games rather than traditional reinforcement learning approaches. And it actually was able to surpass the human's performance on 3 of the games.
Okay, now let's go into that, what the deep Q network is. So remember, when we did regular tabular Q learning, the objective was to use something called value iteration, the Bellman optimality equation, to converge on the optimal Q value function. With deep Q networks, we do this a little different. Instead of using value iteration, we use a neural network to approximate the optimal Q value function. So what exactly does this mean? What would this look like? Well, as Ishu mentioned earlier, the inputs into this neural network would be some state, let's just call this state S. And the neural network would just interpret the state. And now let's look at the outputs. Say in the state S, there's a maximum of 7 possible actions to take from the state. That means there would be 7 outputs in the final layer. And each output corresponds to the estimated Q value of taking each action in that state S. And I say estimated because the optimal Q value function is what we're trying to learn. What the model is actually outputting is its best guess for what the optimal Q value for any given action is. Just briefly, the model architecture described in the paper is the first 2 layers are convolutional layers because, as Ishu mentioned, we're passing in the raw image input of. Okay, sorry about that. We're passing in a raw image of the game that we're trying to solve. For example, you guys all know Pong from Atari, right? The Pong game. An example input would be we just crop out the actual Pong game, like from the arcade screen, for example. We pass that in as a state into our network. The convolutional layers will help interpret that, and those are followed by some fully connected dense layers, which will eventually output our Q values. I promise we're almost done. So now that we kind of understand the architecture, let's take a look at how this model is actually trained. How do we make this model learn the optimal Q value function? Well, first let's look at something called replay memory. As our model progresses and trains, in any given time step, it is given a state. It determines which action to take in that state. And based on that action, it transitions to a new state and it gets some reward from the action it takes, right? So we stored everything I just said into a tuple. And you can see that there, S, A, S prime, R T plus 1. S is the state that we input into the model. A is the action that we have determined to take based off that state. S prime is the new state we transition to, and RT plus 1 is the reward we get from taking action A in state S. So, and we can store as many of these experiences as we like. For our model, I think we stored the last 10,000 experiences, and they're just all consecutive. All right, so how do we use this replay memory? How do we use these experiences? Well, let me try and explain it this way. All right, so our experiences actually make up our entire training set. Our experiences are our training data. That's what These are what our models learn. And how to do this? Well, let me explain it by explaining the loss function we see here. So at some point in a time step, we sample a batch of random experiences from our replay network. And for the sake of simplicity, let's just say we have a batch size of 1. So in our example, we're just sampling 1 random experience from our replay network. What we do is we pass in the state S from that experience that we sampled. We pass in that state S into our network, which we call a policy network, into our DQN, which we call a policy network. And then we get outputs for the Q values of each action we can take from that state S. We look at the outputs, we see which output corresponds to the action A that was stored in that experience. And we take that estimated Q value. That is what our model believes to be the optimal Q value for that state action pair, for that SA state action pair. Now, we don't know if that's actually correct. So we need to calculate loss. And what do we use to calculate loss? Go back to the Bellman optimality equation. Remember, this is exactly what was on the previous slide for the Bellman optimality equation. That describes the actual maximum and optimal Q value from taking action A in state S. So how do we calculate this? Well, as you can see here, our T+1, remember, that's already stored in the experience tuple. So we already have that. The only problem now is to calculate max Q. And how do we do that? Well, remember, we also have S prime stored in our experience tuple. So all we have to do is plug in S prime and pass that again into our policy net. And what that max term means is we just look at the outputs for the actions and Q values of each action for S prime. We just take the maximum one. And we just plug that back into this equation and we can calculate the loss, do backprop, whatever. That's all standard stuff. And now there's a problem with that because in order we use the same weights in the same network to calculate our estimated Q value and our optimal Q value, right? And that's a problem because as backprop is being conducted, those weights change, and therefore, as our estimated value changes, so does our max value change. It's kind of a moving goalpost thing, right? If say we make a change to the weights that causes our estimated value to increase by 1, that's an arbitrary example, then because those same weights are used to calculate this max term, maybe the max term is also increased by 1. So it's kind of a moving target problem. We're using the same network in both areas, which is a problem. So just briefly, what we do to solve that is we create a copy of our policy net called the target net, which we only update the weights for every couple of time steps, so that the weights in the target net will be different than the weights of the policy net. The target net will be used to calculate the max Q value, and the policy net will be used to calculate the estimated Q values. So in this way, we're using different weights to calculate both values, and the goalposts are more stable. Great. Let's just skip this.
Don't worry about it. It's just like exactly what he said, and then ordered steps. Yeah, don't worry about it.
Oh yeah, I still need to talk. Okay. So that's the theory. Practically, what do we do this semester? Well, so our first step was to understand DQN, understand all the stuff I just said, and in order to do that, we thought it'd be a good idea to find an implementation online of the DQ network that we can analyze the code for. We did find one implemented in PyTorch, and the example we found used the DQ network to solve the Cartful OpenAI gym environment. If you don't know what Cartful is, it's kind of a game you see here. The cart is this black square, the pole is this pole. And essentially, the two actions you can take are move the cart left and move the cart right. And you're just trying to keep the pole balanced on the cart for as long as possible. So the reward that we used, or that was used for the cartful environment, is essentially how long we can keep the game running for without ending. Because the longer we keep the game running for, that directly correlates to how long we kept the pole up for without falling over the game, right? So we optimized for duration of game. And that worked out pretty well. We got good results. Next, we wanted to see if we could recreate some of the results in the DeepMind Atari paper that Ishu was talking about. So we chose one of the games that the researchers in that paper tested on, which was Pong. one thing we forgot to do was change what the reward function was looking for. So our GPQ network optimized for duration of game, which is not really what you want to do, but it's a simple fix to change the reward function to something more accurate later. But the ultimate goal to understand how a DPQ network works was accomplished.
And no, it should be an easy fix. You think about it, palm goes up to 21. You can run the game as long as possible at 21, 20. And for our data set, the output was very consistent. The result was always like 600 seconds for the game, I think. So yeah, that's good stuff. But as for Grid World, which is essentially a simple implementation of a problem or representation if you think about it. So by nature, ocean currents are very continuous, but when you break it down to small grids where plastic can traverse, it naturally becomes a grid world problem. If you think about like this, we have plastic from this location going to another, that can be considered as the reward or negative reward. And that reward can be created from the data set that we're going to talk about later on. Essentially, the agent is going to decide that we have this plastic, where do we dump it? Based on the data set, it should petition 25% here, 10% here, keeps going to this location and another location, therefore collecting negative rewards, and we want to minimize that negative rewards, making it as positive as possible, which intuitively means keeping it very local or away from endangered species natural habitats, or just locations that are more inclined to have people pick up and clean up, because there are things that we can really account for. Therefore, we use ocean parcels. We're going to put in the data set into ocean parcels, which uses ocean currents to simulate where the plastic trash should go, creating a grid world environment where we can deploy our agent.
Yeah, and just to summarize really quickly in a few words, what the agent in our new game is trying to do is figure out the best places to drop trash to minimize the spread of ocean pollution, bringing those places trash into ocean waters. Actually.
All right, so onto the data set. So we have a paper from the United Nations, quantifies and maps global trades across the entire life cycle of plastic for everything from the raw input stage to the final product to plastic waste for anything like that Chipotle bag you might be using, paper plates, and potentially, like the production. And the database is created by these two institutes. I don't really know what they are. They're probably important. But what they do, and they do a really good job, is they have a lot of data. They draw the official trade classifications of plastics. They compose that whole big set of data on inputs and products. So what we need from that, we need to essentially parse the paper, get the global flow of plastic trade, and therefore we know, all right, how much plastic goes to this nation from this nation. And then we can put that into our reward environment and therefore create something that has reward for every local squares that we partition. Ocean movements, of course, will be simulated with ocean parcels, and that shows where the plastic should be going, showing our reward essentially. Okay, on to the next steps. That's a lot of data to work with. That's a very big environment. And we've been talking to the professor leading the project, and he's giving us $15,000 worth of computational credits on Azure. For future use, ocean parcels will be very expensive on our computer. Therefore, we want to move to a cloud-based environment with more powerful hardware as well as systems. And training should take significantly less time on these powerful systems instead of our, All right, just to wrap things up, that's it for our presentation. Any questions? Please don't ask. Thank you.
What was it like working alongside Sam?
What's the question?
What was it like working alongside Sam?
It was an amazing experience. Yeah.
Any other questions? It was a lot.
Great, thank you, everybody.
Up next, we have one of our presentations that our curriculum members actually made. So they, at the end of their curriculum, rather than looking at a paper, they decided to use Dataset and create their own little concept.
Okay, everyone, so this is our presentation on using AI to differentiate between real and fake news. I'm Natalie, I'm a sophomore CS major.
I'm Leslie, I'm a freshman, I'm a CSE
There's
major.
7 chickens.
All right, so there are 3 different types of fake news: misinformation, disinformation, and malinformation, which are mostly differentiated between the intent behind the fake news. This is a term that's become increasingly controversial over time and runs the risk that reading news might actually make you less informed than not reading the news in the first place. The articles we are looking at are mostly differentiating political fake news, whether that was fake or true. Example true articles are U.S. military to accept transgender recruits on Monday. An example of a fake news article was drunk bragging Trump staffer started Russian investigation. So obviously it's more sensationalist in nature and draws conclusions which are not necessarily based on facts.
So generally our goal was to find, like, due to the danger and hysteria that fake news publications can cause, our goal for the project was to apply natural language processing and a logistic regression model to a data set complete with a selection of both real and fake news. And our project aimed for solid detection of fake news in the sea of different headlines.
So we used Kaggle's fake and real news data set to run our data. It had a fake.csv and a true.csv, which were classified respectively. Each file contained a few different columns of information, including text, title, subject, and data for various fake or true articles. But we only used the title and subject, title, text, and subject, the date, and I think there was one other variable we didn't end up using just because they weren't relevant to what we were doing. It should be noted that these articles were mostly gathered from 2017, so our model may not work as well from current or like way previously past articles.
So during our exploratory data analysis, after loading in our data set and making sure that everything downloaded correctly, we proceeded to combine all of our news entries into a single data set to make processing way easier. And we also gave them binary labels. The data set was organized and dimensions were collected.
We used regular expression and natural language toolkit to process our data. We took out stop words, which were words we don't really care about in our data, such as the, and, is, it, words like that. And then we also stemmed words, which is just taking the root of the word. So words like liked, likes, and likely were just reduced to like. This just made the data more organized. So then we used count vectorizer to select the most 5,000 commonly occurring words and fit transform to make them into a document term matrix. We then put this into our logistic regression model.
So the data set was split into a 75-25 ratio of training and testing data, which was considered an ideal ratio for pattern recognition. We modeled our data using logistic regression, which is a technique that models probability. We imported it from the sklearn linear model to fit it according to the training set. And a confusion matrix was made, which visualizes how well our detection is working, which we can see here on the right. And it was plotted using pandas. So our accuracy was 94.96, which was a little bit better from we were expecting, but not as better as we wanted to. And it was calculated using the sklearn metrics accuracy score, which checks if a set of labels predicted for a sample exactly matches the corresponding set of labels that it wants it to match. So,
And this graph right here further explains this one. So these are true positives, false negatives, and true negatives.
and as we can see here, our model performed worse on true data as it identified 310 articles as fake when they were in fact true, compared to the fake articles that were only 100.
So here's just some more information on our findings. Our values for precision, recall, and the F1 score were pretty ideal to us. We were generally impressed with them and happy with these results. We did a lot of different adjustments, adjusting the training set to the data set ratio, the 75-25 ratio we talked about earlier, as well as the commonly occurring words. We went with 5,000, but we tried a few different numbers, and these were overall the best precision and recall values we could get. And yeah, this is our project on exploratory regression.
Questions?
Can you speak a little bit more about the logistic regression model you guys use? Because like 94% on fake news, real news detection is like, that's really good.
It was so, well, it's just stuff back here, but a lot of it was done with like imports and packages. So the main one was the sklearn like fit transform that I talked about earlier. That just transformed the data, and then we just plugged that into a logistic regression import also from sklearn, and that kind of did the most of the work for us.
Yeah, and the accuracy of course was also.
Then also you guys said that you used like specific keywords, like out of, we looked at like the words. So did you look at the words separately or did you look at them in like
We did look at them separately. So first we took out the stop words, then we stemmed each word, and from there it just created like the most commonly occurring words. And I think that is how then it was used with the imports to like classify those most commonly occurring words, whether they were true or fake.
So like the insight you guys got out of this model was like what words are commonly used in.
Yeah, you could print the most commonly occurring words. This was just classifying them more for like, because this was our first project, it was just like, can we get this off the ground? Can it do something that we think is meaningful?
Yeah.
Yeah.
What we generally notice with the data is that if a title is considered fake news, even if the actual like information, let's say it's based on a real event, if the way it's presented is using many words that are very emotion-based, sensationalist vocabulary, then it would be marked as fake news because it could give people the wrong impression, which is not at all what would be considered like factual reporting. And that is also a reason why got rid of words like likely, like, and other like irrelevant words, more emotionally charged words.
Yeah, and I think that's also why, if you go to this slide, why this value is kind of high, because it's just based on the words they use. So it's in a way just looking at like sensationalist words versus like more like stereotypical like news words that are unbiased.
Any other questions?
Do you have any insights into what worked to improve your results? For example, just changing the number of words from 5,000 to some other number.
Yeah, we actually did a little bit of work in that. We did like 3,000, 35, 4,000, and kind of like did a range around 5,000. But 5,000 was the best value we found, which being new to AI, I'm not really sure why in particular that was the best. We also messed around with the ratio a little bit. The 80-20 had 80-20 had good results too. This was only 0.01 better, but we figured we would take the 0.01 and kept it at the 75-25 ratio.
Yeah, definitely in the future, we expand more on this project. It would be interesting to include fake news, real news data from more recent years. Now that the kind of scope of news sometimes is less political, because most of, actually a large majority of our data was just mostly political headlines based on specific politicians. So we definitely want to see where a model goes using more recent data.
Follow up on the question that before going on to other data sets, the first thing I would do is, if your results with a simple model are so high, you should not just be like, oh, AI is so great. You should be suspect. So the first thing to do is actually to see whether these results are not suspect. Suspect meaning, like, you just first explore your data. You look, for example, at the term frequency between the negative and the positive class. If there's like, some words that essentially appear 95% always in fake news, then a simple counting model would have done just as good as an AI. So then that that will basically tell you this data set is not a good data set for an AI approach because it's simple enough that even a simple just kind of pre-processing stats approach would work. So I think that's the first thing to look at.
Yeah, that's an interesting approach. I actually wouldn't have thought to do that next. So
So always, like in any AI project, first you explore your data. Before you start applying any model, you have to like get to know your data. Like visualize the distribution of features, the distribution of labels, make sure that you understand what's in there. I think that's very important. And then once you have the model, understand your model. If you're using a logistic regression, then it's a very simple thing. Just look at the coefficients of the words to figure out which are the most important words that the model is using to predict. And that would also give you a lot of insight about, has it actually learned something meaningful? Or maybe there is like, I don't know, the name of the site from where it comes. And there's some sites that only have fake news. Maybe it has learned something to recognize something like that is secondary, but it doesn't actually correspond to using the language to understand the difference between fake and news.
yeah, that's also interesting because I looked into where the data set got its data from. And they had a few like journals that they cited, but I couldn't figure out where they actually got the titles. And that also was not like a column that was given in the data set. So that is a good thing to think about. Yeah, obviously where you get your news does matter a lot.
Yeah. Thank you.
Thank you.
All right, get settled. For your next group of work project X, our topic is on I'm project. Woo!
I'm Shanti.
Victoria.
And I'm Jordan. So just a quick intro, what is Project X? Project X is University of Toronto AI group. They run Project X competition every year. This is their second annual Project X competition. We participated last year. They invite schools from all around North America and some from South America and Europe to participate in an international AI competition based on a certain vertical that they choose every year. This year's is health. So they give us 3 options for verticals you can choose: epidemiology, clinical practices, and genetics. We chose to focus on epidemiology. It just interested us the most. So for this competition, we basically have to submit a proposal, choose a data set, and then subsequently write a paper by the end of about 6 months. And so our paper is due at the end of January, following which we will be at their AI conference in February. So there is up to $75,000 in prizes from this competition. So we're hoping to bring some home for USC. The purpose of our project, though. So in many countries, outbreaks of mosquito-borne diseases, so things like malaria, yellow fever, dengue fever, etc., are still very common. And this is particularly bad in tropical countries where they have climates that really are great for mosquito populations to breed and to grow significantly. And because of these bigger populations of mosquitoes, it can put a significant strain on the healthcare systems there. And there can be quite a battle for resources in different places since these outbreaks are very quickly happening and hard to contain, especially since mosquitoes can fly wherever they want. And then as climate is changing and we're getting more and more tropical areas in the world that have these climates, populations, there are increases of outbreaks of mosquito-borne diseases. So something to worry about.
All right, so we decided to use mosquito as our main vectors because mosquito-borne illnesses are very prevalent in the places that we're looking at. And something that's very interesting about mosquitoes is their disease outbreaks are seasonal. So in these places, when there's high rainfall, which happens according to the season, you're going to get more mosquito outbreaks. And also in a lot of these places, like mosquito-borne diseases like malaria, yellow fever, and dengue, are like endemic. So they're going to happen all year, kind of like in these places the mosquito virus. So what happens is when it rains, puddles of water will form on the ground, and that's when mosquitoes can breed. Because mosquitoes have a very fast breeding time, when it rains, we're going to have a malaria outbreak because when there's more mosquitoes, there's going to be more transmission of these mosquito-borne illnesses. Yeah. Oh, sorry. And so then for prior work, there's been a lot of prior work. So like I said, there's been a lot of work correlating rainfall with like temperature and these mosquito-borne illnesses. So in this paper up here, climate prediction of El Nino malaria epidemics in Northwest Tanzania, researchers used regression analysis to predict this like the malaria epidemics in response to El Nino. So as you can see in these graphs, incidences are correlated with rainfall as well as maximum temperature. And then there's also been work now more recently using AI instead of just like regression models, deep learning. So in this work, we're predicting malaria epidemics and looking at possible they use random forest generators along with malaria to predict malaria cases using precipitation data. So that's where like rainfall is correlated with malaria incidents. But importantly, in these models, they tend to focus on one area. So the one using deep learning only used a 13-week a 13-week period, and for one healthcare facility rather than like an entire nation or entire like country or entire like climate. So they're very specific to a certain time period or a certain like area.
Cool. So for the data gathering and or process, so for our data sourcing, it was pretty difficult to find data sets for like specific data sets for large areas, especially considering that a lot of these areas that are affected by malaria and dengue don't have robust systems to collect a lot of the data. So many of the outbreak data sets that we found were very sparse. They either had just outbreaks over time in regards to the months or weeks, but they didn't have anything on weather or any of the geospatial factors that we wanted to look at or anything like that. Also, we were looking at climate versus weather. The reason why we chose a 10 to 30-day process rather than a long climate prediction was just because we thought that that would be one, better for the people using these models for like their predictions, but then also two, because the model could be a little bit more specific and we could find better data to train without stress.
Yeah, so we eventually did find some data. And so for malaria data, we ended up focusing on the area of Odisha in India. So Odisha is a state in the central eastern part of India. So it's a coastal state. And in 2016, it accounted for about 40% of the malaria burden in India. So you might be wondering, like, why does one state account for so much of the malaria case in that country? There's a couple of factors. One, out of the 36 states in India, Odisha rates 32nd on the Human Development Index. And additionally, it experiences 2 rainy seasons. So it's kind of a combination of multiple factors that makes it a perfect breeding ground for malaria to proliferate. And so it's in the interest of the Indian government to study why malaria propagates much in this state. And so the Indian National Vector-Borne Disease Control Program conducted a study over 2003 to 2013, collecting cases of malaria data in that state, and it's segmented by district. And so this is one of the best data sets we found for, it includes some level of geospatial information in the sense of districts, and it also contains over an 11-year time period. For weather data, we use the Google Earth Engine API, which is a system that contains a bunch of databases, climate models, just geospatial information generally. And so we employed the Terra climate model, which is from the University of Idaho. It provides interpolated climate data across the whole world. And so we use that to get minimum and maximum monthly temperatures along with precipitations for the districts of Odisha from 2003 to 2013. That's what we'll be using in our model.
So moving on to modeling. We're going to start off with Arima and Arima.
Yeah, so the first modeling technique we employed is Arima. So Arima stands for autoregressive integrated moving average. And Arima is a seasonal variant of that kind of model. So essentially what we're dealing with in this problem is a time series problem. And so Arima is a technique for performing time series forecasting.
There are three main aspects of these types of models. They're the autoregression, integration, and moving average. I'll explain them all. I'll leave integration for the last because that's kind of what makes Arima unique. So autoregression and moving average are both two types of modeling techniques that rely on previous time steps in order to perform the next one. And so autoregression specifically, if we have they use something called a lag order. And so if an autoregression model has a lag order of 6, that would mean that if I want to perform forecast at time step t plus 1, I would, if the lag order of 6, I would refer to the previous 6 time steps. And with regards to the moving average model, it's similar in that it refers to previous time steps rather than referring to the data itself. It refers to a white noise error term. But essentially, both autoregression and moving average are regression-based models that predict into the future. And so the integration step is what makes Arima unique. Traditionally, autoregressive moving average models only work with stationary data. The stationary data is data where the distribution of the data is the same across time. In the graph that we see here, we can see that there's a downward trend in the malaria cases. In Odisha, this is because of actions on the part of the government to increase awareness about malaria, and just generally as the development occurs, the cases are going down. So we would call this a non-stationary data set. And so for traditional models like autoregressive moving average without integration, modeling would yield very poor results. And so what the integration step does is it makes non-stationary data stationary by the use of differences. And so differences is basically just like if I have a difference order of 3, what that means is that at each time step, I would subtract. So if I have time step t, to perform a difference of 3, I would refer back to the previous 3 time steps and then subtract. And through this process, you can make non-stationary data stationary. And that's what we employ for the Arima modeling. But additionally, we observe a seasonality in this data set. Actually, if you look closely, you'll notice that every year there are 2 spikes. Those correspond to the 2 rainy seasons in Odisha. And this seasonality also has to be accounted for in a similar way. And so the seasonal Arima model has additional moving average and autoregressive terms to account for the seasonality. So this is the type of model we employ. So as for the results of our Arima modeling, we found that the best time period for training was to refer to the previous 60 months, so about 5 years. And so the average absolute percent error in terms of the case predictions is 18.71%, which is not bad, but it can definitely be improved by further tuning the parameters. The parameters were selected for the Arima model by referring to the autocorrelation plots and also partial autocorrelation plots, and then also doing like a grid search on the proof space. But definitely it was by no means an exhaustive parameter search, and there's a lot of room for improvement. But the reason we opted to use the Arima and S-Arima just because we can sort of serve as a baseline against which we will compare our more sophisticated techniques.
Yeah, so we also explored Varma, and I'm going to explain what that is later. But essentially, the reason why we did this is essentially with Arima, you can only look at one time series. So in this case, it was cases, right? But as you can see from other research, mosquitoes are also highly correlated with the weather. So we wanted to include that with our Varma. So Varma is vectorized autoregressive moving average. So it's slightly different from Arima. But essentially what you need to know is it combines vectorized autoregression and vectorized moving average. It combines them together so you can consider lag order as well as the moving average. And then the S is just the seasonal part. Because weather and mosquitoes are seasonal, we want to also look at those parameters. So in other words, we use Varma to linearly forecast the integrated variables. So in this case, it'd be something like weather factors like the precipitation, humidity, temperature, as well as malaria cases. And so the main difference between Varma and Arima is Varma is almost like a generalization of multiple time series. So so it can look at multivariate time series, which are essentially like a certain time series that includes multiple factors. So in this case, climate and so here is our data for our S-Varma. So the first row is when you look at temperature, precipitation, and cases. And so the absolute percent error, which are residuals, as a fraction of our prediction, and that is. Then we also looked at temperature and cases. The reason why we did this was because we wanted to like separate temperature and precipitation. In some papers, they only look at temperature, and other papers they combine the two. So that's what we have there. So essentially, The biggest takeaways from this is it is rather computationally expensive to fine tune all the parameters. We have both the regular order of the time series as well as the seasonal order, which is, and because Arima is, it can take a long time to run, it takes a long time to find the two parameters. As well as other kind of models that we ran, there's evidence that transformation on raw data can improve the percent error. So if you like raw transform cases or like essentially like squish the data, like sometimes the absolute percent error can decrease. But right now, this is just the predictions on raw case prediction, raw max temperature, and raw like precipitation.
Perfect. And so following these more statistical models, we decided to look more into deep learning to assess these patterns over time. We specifically looked at LSTMs, which are long short-term memory networks. So it's a specific type of recurrent network, which has a feedback connection rather than a feed-forward connection for data, which means this is really good for learning order dependence. So with these time series that we have, it works very well to see those trends over time and predict how they will continue and how each step will continue based on everything before it. So it also works very well to process these large sequences of data at once. As we were talking, we have data from 11 years. So we have both the weather and the outbreak data over this period of time, which is a significant amount of data to relate at once. So it makes it ideal for us to look at these longer periods of time with one large model. So in essence, how it works, every cell in an LSTM has like the cell body plus 3 other gates. It's going to have the input gate, the output gate, and the forget gate. The cell basically stores the memory over an arbitrary period of time that's fed into the LSTM. And the gates are there to determine what goes into and out of the cell and how you alter that value over time. So it takes the values of every prior step and weights them accordingly to give you the new output for a next step in the sequence. So as we had mentioned earlier with how our data looks, and it's these 2 large time series with weather and with outbreaks cases, we fed those into the network. So similar to the other one, we tried with temperature, precipitation, and cases, and then temperature and cases. So while it's not the best absolute error or accuracy, it is an improvement from both of the other statistical models that don't use deep learning. And the fun and easy part with long short-term memory networks is that unlike Arima and Varma, you can very easily tune hyperparameters, and they do use gradient ascent and descent to tune these parameters as the model is training. And so it's a faster way to find for ideal networks. And in addition to that, to tune these hyperparameters rather than having to singularly switch each of 6 parameters within Varma, it's one that is automatically done as part of the network. So while these aren't the best accuracies initially, this was a baseline using a vanilla long short-term memory network. So it had 3 layers of LSTM, and that was all, which leaves a lot of room for improvement. And we'll continue on.
Yeah, so something that we were looking into using in the future is classification models instead of just regression models. Those of you guys who don't know, the difference between a classification model and a regression model is a regression model allows for quantitative discovery over a period of time, whereas a classification model categorizes that data into some type of like category. So in our case, we have an outbreak criterion, and that outbreak criterion is a 10% positive deviation over a 6-month sliding scale. So basically what that means is that we would look at the 6 months prior to that of the month that we're at. And if the predicted value would have a 10% deviation, that would categorize an outbreak or not an outbreak. So one of the things when we were looking into this was the benefits of using a model like this in Iran. For influenza-based viruses, deep learning networks like ANNs and SVMs outperformed Arima, and other models like root mean square errors and mean absolute errors. So we thought that this could potentially be something really good for us to use. And then two models that we're looking into using in the future is time series forest classifier, as Jordan was saying earlier, and shapelet-based classifier and shapelet transformation classifier. So our next slide, we tried the Canon with dynamic time warping, and we didn't get the best values or the best results out of that. So I didn't think that it was valuable for us to even talk about that. That could have just been a problem with teaching. But one thing that I did want to talk about was the shapelet-based classifier and the shapelet transformation classifier. The way that this model works basically is it looks at the category of the overall data and creates individual shapelets that are then later matched and used for predictions over the future data. So if it fits within that shapelet, then it would classify as said category. Future steps for this project. We have to basically choose what our best performing model will be. So we're really early on. We still have another 2 months in this project. So we wanted to try out multiple different models, play around with more data, find more data, and once again, just keep on looking around. If we're unable to find the results that we actually are looking for like the overall data, we may start to combine our data sets and combine our models. So that way our outputs could ultimately, we would have like different models for weather prediction, for geospatial, and then combine those features together. And finally, once we build out this model for Adisha, we would want to implement transfer learning to apply to different areas.
Yeah, and just to build off of what he said a little bit, as far as combining outputs from different types of models, things like Varma are very good at predicting temperatures in the future. So we had it between a 0.8, like plus or minus 0.8 was the prediction. So it was very accurate on the prediction for weather and temperature side, but not very accurate for cases. So ultimately what we could do is take the weather prediction from Varma, take perhaps disease prediction from an LSTM or another type of network, and aggregate them together to form a new prediction based off of both models. And then in addition to transfer learning, how we would implement that is finding similar areas with similar climates and geospatial features to allow for a more regularized geographic data collection, where we can predict these sort of tropical disease outbreaks in other places that aren't necessarily where our data set was from, because as we mentioned, that data is very difficult to find. But it could help predict these outbreaks in some other places that have similar climates.
Cool, yeah, so this is just our timeline for the future of the project. So like I said earlier, we have until January where we're going to train with new hyperparameters and try new models like we were saying earlier. And then finally in February is the actual conference where we'll be going into.
Favorite quote from project meeting.
So, what is your look ahead that you're predicting it?
Sorry?
What are you predicting? Like how many steps, how many days ahead are you predicting?
1 month.
1 month. Yeah, so approximately 4 weeks.
Okay, so you're using the data from like, let's say today and the last few days of today and predicting like what will happen in 1 month's time?
It's the data we have is
Monthly?
So we
So
use
this-
the last several months.
The next month.
Yeah, so we're using, in some cases, we're using different numbers, but the base for what we used was 6 months, the previous 6 months to predict.
And when you're predicting the next month, are you using the weather for the next month or not?
For Varma will output predictions for everything. So it could output a prediction for temperature as well as cases. So,
But does it use that in the predicting of the cases?
No, it doesn't.
No, the LSTM does though.
The LSTM does what?
The LSTM uses the predicted data that we have from our network as well.
In predicting the case.
It uses the predicted weather.
Yeah.
The prediction of the case.
It uses okay, and where do you get the predicted weather for the LSTM?
The predicted weather for the LSTM, part of it is from our model. So we feed that in along with the data from the Google Earth engine. So we have both as inputs to go into, so we can compare like actual versus what our model was predicting.
The only problem is that like we'll get a little bit of bias from that. So we're trying to think of like a way around that. But like our best bet right now is using like the weather APIs to use like their predicted weather, because we couldn't find the data sources that allowed us to both have weather predictions for the specific area and the malaria cases.
I see. But at least for the time being, you could just assume like the real weather was like predicted perfectly and use it.
Yes, we tried both ways. And they both performed about the same, just on an initial test for a baseline.
Then is it the case and then all these three models that you reported on cannot be compared to each other because they're all like kind of trained with a different amount of information?
Yeah, we kind of wanted to see what the baseline was with the different amounts of information to see whether or not a statistical model was accurate enough so that we could just use that with.
I guess what I'm asking is, for example, if I look at Arima versus the Aroma model, can I compare those two numbers apples to apples?
In this particular instance, no, because the Varma data comes from a particular test in our particular region in the Odisha.
Okay.
The Arima data comes from it's only based. The Arima is only predicting disease outbreaks, right? And so I aggregated across the entire state for the Arima. But because the Varma uses weather, the aggregation is impossible.
So then you could at least run Arima on this particular region.
Yes, absolutely.
It would be useful to have a sense of that.
In future, we want to, like the statewide Arima was just sort of a baseline. We want to have like district by district modeling, and then hopefully that'll yield better results to include some kind of like spatial resolution as well.
Yeah, so just building off of that with that spatial resolution, our hope by the end is to have this region by region predictions, and from that extrapolate to see how like an outbreak in neighboring regions might affect its neighboring region.
So you are going to try some spatial temporal models?
Yes.
Yeah, and we'd also like to incorporate like demographic information as well.
Yeah, so we've been looking at literacy rates and other things like that, quality of living and gross money per capita to include as another metric down the line.
Awesome.
What about instances of sickle cell anemia?
Yeah, we consider that data is not publicly available. And we're looking at other diseases as well, besides malaria. Malaria was just the easiest data set for us to start with. We considered that though, because malaria is very dependent on genetic factors. But from what we're seeing, it's sickle cell anemia is not as prevalent in these areas, just based on the high rates of malaria. Yeah. Anything else? Great, well, thank you all for listening. All right, so up next, we have a presentation by a student from Professor Delfinia's Comp Sci 461 class, which is AI for Sustainability. So he's a CAIS++ member as well. He's going to be presenting his project from the class from all semester.
great introduction. So yeah, I'm Isaac. I'm part of Professor Delpino's CSI 461 class. And so my team, the rest of the team members couldn't be here, but our project is predicting California high school graduation and post-secondary enrollment rates based on socioeconomic and community-based factors. And so just for the agenda for today, I'm going to be talking about the problem statement and then some background on the problem, how we prepared our data, the models we used, and then the results, some optimization we were able to do with those results, and then actually I cut next steps for time. But so some background on this problem. So as most people know, education is really important. And in 2018, 258 million students dropped out of high school worldwide, and in the state of California, about 64% of high school students ended up going to college, and then about 84% of high school students ended up graduating. And so the incomes for people who graduate high school are about $8,000 more on average than those of people who don't. And then the income for people who finish college are about $32,000 more on average than those who just finished high school. So basically, education is really important. And so some past work on the subject, people have looked at things like GPA and standardized test scores to try to predict how students will do. Other people have looked at things that pertain to the teachers, like how long the teachers have been teaching, how much they make, their education. But what we're looking at is we have basically two types of data that we use in our analysis. We use data that's on the school level, so characteristics about the school, and then community-based data. So that's census data about the area around the school. And we're using that to predict two things. High school graduation rates and college enrollment rates for a given high school. So yeah, just a little diagram here. We have our two types of data that go into our ML model. We have two predictions, and then we do some analysis with that. So as for the data preparation, I'm not going to go too deep into this, but so like I said, we take school data. So we pulled that from the California Department of Education, and you can see here some of the things we pulled were benchmarks for certain tests, absenteeism rate, and bilingual certificate rate, and some other factors. We pulled these for 1,940 high schools in California, and you can see here. Now, the second type of data we used, as I said, was community-based data. So that came from the American Community Survey, and we pulled that via Social Explorer. And with that data, it is aggregated with the in the area contained by the attendance zone of the school district. So basically just the area around the school district. It reports these metrics. There are 25 features in total, and the general types are income, race, employment status, population, etc. And then the distribution of these labels. So you can see that for college going rate and high school graduation rate, they're both left skewed, meaning that most schools have pretty high rates, but there are a few where they're lower. And you can also see that it's more spread out for going to college, which is what you'd expect. So data preprocessing, I'm gonna kind of glaze over some of this, but we just combined the data and dropped some features that had strings for their values, and then we dropped some schools that had NaN values. So what we ended up with was 1,544 high schools that we had data for, with 48 total features, 25 of those being community-based and 23 of them being on the school level. So how we trained our model and the data that we put into our model, again, we had 1,544 schools. We were predicting college going rate and high school graduation rate, and we did an 80-20 train test split. So now for some of the results. So when we tried to use just census data to predict our targets, it did not do well at all, 0.21 and 0.28 for the linear model. And you can see a lot of these important features have to do with income, also population, and some others that you can see here. Now, when we use just the school level data, we did a little bit better. We got 0.69 and 0.64 for our square values. And you can see that in both cases, actually the absenteeism rate at the school was the most important factor for both of our metrics. Now, when we combined both types of data, we got much better results. So 0.86 and 0.77 are square values. And something to note here is that all of the most important factors from this permutation importance are all community-based. So what that suggests is that maybe the community in which a student lives has more impact on their success than what the school can actually do. And that's really interesting. So these are the 6 models we used. And you can see that for predicting college going rate, the random forest did the best with an R square value of 0.89. So pretty accurate. And these are just some plots of the predicted Y versus ground truth Y. Random forest in the middle did the best. So you can see it's a tighter spread than some of the other models. So same thing with graduation rate. We did the same analysis. And again, the random forest was the best. So that had an R square value of 0.94. So that did really well for predicting graduation rates. And again, you can see these plots. You can also kind of see here the skewness in the data, how most schools had high graduation rates. So now the effects of some interventions. So what we did here is we trained the model, and then we took all the data and we decreased chronic absenteeism for every school by 5% and then 10 and then 15%. And we looked at how the graduation rates changed when we did that. So you can see that when we decreased chronic absenteeism by 15%, on average, the expected graduation rate went up by about 0.2%. And then these were the next 2 most important features. They had less of an impact. And then for college going rate, it was, again, chronic absenteeism is number 1, and then these 2 here. It made more of an impact. So when we decreased chronic absenteeism by 15%, we had about a 1% increase in college going rate, estimated. So just some points about what we sort of did here. We identified the top features that impact student success for both grad rates and college going. So the top overall feature actually was just the population contained within the attendance zone of the school district. So that was interesting. And then the top changeable feature, so the top feature on the school level was chronic absenteeism. And so what that means is that by decreasing chronic absenteeism, that is the changeable factor that we looked at. That was the most important for both of our metrics, meaning that we could now advise schools that if you're going to try to change one thing to help your students succeed, it would be getting them to go to school and not be absent. Also, through analyzing how these rates changed with increases and decreases in certain features, we can inform school. So I said. That is it. And if anybody has any questions, I will take them.
Do you mind re-explaining the top overall metric? Like you said it was population.
Yeah. So if you look here, this is when we ran all the combined data through our model, and you can see that the permutation importance for both labels says that population is the most influential factor for student success for both metrics. So we don't know exactly why that is, but that's just what the model told us.
So about that population, I'm just curious if that was like inversely correlated or directly correlated, like higher population means higher graduation rate. Or
Oh yeah, so that was positively correlated with both.
Can you clarify, how did you come up with those feature importances?
So we just used like I think it was the sklearn implementation of permutation importance. students. So, yeah.
And the best performing model was random forest, right?
Yeah, so that was one thing. We were having some trouble making it work with random forest. So for this, we used the linear model. So our square values were a little lower for this. And it's something we plan to improve on later, because this is an ongoing project still.
So the table with the performances for random forest, XG boost, was it not for the same problem?
It was for the same problem.
And
Just the permutation importance is not reported for them.
okay. Yeah, I was just wondering, like, if you look into the feature importances for the best performing model, if it would match with the report.
That's what they have to do in the next 10 days before the final project report, right?
Yeah.
Isaac?
Yeah.
Okay.
That's the immediate next step.
For the next step, have you tried looking into chronic absenteeism, what the reasons behind it? Perhaps chronic illness or having to work during the time that you're in school?
Yeah, that's a good question. So we haven't started looking into that yet. Maybe if we have time, we might look into that. But yeah, that's definitely a good point. Like, yeah, if it's something.
Because it might not be changeable.
Yeah, exactly. Yeah, it might not be changeable. So yeah, we could definitely look into that. I don't know if there's data about like the reason for absenteeism. That's something actually we'll look into, because that would be good to know.
Correct me if I missed this, but did you find a correlation between the median income of a household and like chronic absenteeism? If there's a connection there?
Oh, between those, we did not look at that. That's also part of the next steps. But yeah, so we plan to look at the correlation between all the different input variables and analyze that and see what we can find with that.
Just curious about the features, like the school level features. Did you have anything about like funding do the schools get? Because I would just think like if population is the direct, like, the most significant feature, maybe that has to do with funding they get from that population. I don't know. I don't think just increasing the population of a region.
So that's actually not part of the data that we were able to pull. We had some difficulty getting that data, but yeah, that's a good point. That might lead to the school having more money for sure. One thing is that if there's a big population inside the attendance zone, you would assume that more kids go to that school. And so that probably means more funding, but yeah, we didn't get that directly.
So last year when I taught the course, one of the teams did a project specifically on funding for schools and how that impacts math and English levels course. You can find it on my course page. Actually, Lina was part of this project. I think she presented it here last year. In ShowCAIS, did she get to present her project?
Which was the project?
The education project from last year, which was on funding influencing the math and English levels course for schools.
Yes.
Yeah, but yeah, definitely it's a but Isaac, actually now that you are presenting it again, I saw second presentation. So the population, is the population on the school level, like the footprint of the school, or the whole district?
So that's on the district level.
So that's a problem. Because think about LAUSD. LAUSD is the biggest school district in the country. It's humongous. So all of the high schools, and it has many high schools inside it, they will all show up the same population. But clearly not all these kids are going to, like if there's 10 schools, you're assigning as if each of those 10 schools has like the thousands and thousands of kids that live within LAUSD.
Yeah, that's true.
So that will be problematic, and and that also means that now your data is structured. There's a bunch of schools that have the same label for population, and another bunch of schools from another big school district that have the same. That's why most likely when you do the permutation importance, now you're randomizing this column, which generally has like a stratified, a structured, and so it's messing up the prediction more than anything else. Not necessarily because that maybe it's more important, but because it's more structured because of the way that you're generating the data. So originally we had talked about you using the footprint of the school, but I guess you guys didn't get that to work.
Yeah, so we couldn't really find like school level attendance
Polygons.
shape files.
Uh-huh.
So up next, we're beginning our group presentation. So most of these are paper review or rapid review.
Hi everyone. I'm Aryan,
I'm Zed.
and today we're going to be just presenting a brief introduction into adversarial examples based on a paper which we reviewed this past week.
Yeah.
So yeah, basically adversarial examples, how to fool neural networks, and many other ML models.
Yeah, so we had a lot of fun learning in curriculum, but we really wanted to understand what are the challenges of applying neural networks and artificial methods in the practical field, right? And so in this talk, what we hope to convey is how we get from a dog to red wine or toilet paper, right? And we really want to learn how to protect against this and what the complications of this are.
So the paper was titled Explaining and Addressing Adversarial Examples. Now, what are adversarial examples? We will be primarily using the example inputs of images throughout, but you should note that inputs are not only limited to like just images. It could be like, a vast variety of like input examples. But in this case, they're only slightly different from the correct examples or the correct inputs. For example, if we have an image of a cat and we alter it by applying, if we perturb it by applying noise to it, that is now an adversarial example.
Yeah, and the thing is, a lot of these models are they're susceptible to these adversarial examples, to these bad examples. And what this creates is something called like a fundamental blind spot. A lot of these models misclassify the same example. And why is this happening? How can we actually prevent this? So we want to know why this happens.
So next up, we'll kind of like jump into like just some brief mathematics behind how this adversarial example and how this issue is created and presented to an ML model. So consider, like this image right here, the dot product between a weight vector and an adversarial example x tilde. So as you can see, it's composed of, the original activation plus the weight vector times some perturbation vector eta. Now, if we break it down to individual inputs, the precision of an individual input is limited. Yet, when we kind of like add eta, a vector, a perturbation vector to the input, and we have to note that the eta itself, the magnitude of this vector is, it's bounded, it's small by some epsilon. And, so individually, it doesn't make a huge difference. But when these inputs accumulate over higher dimensions, so like, more features which we input into the model, a small change in input can add up to a significant change in the output activation.
Yeah, so essentially what's going on here is we have an input X and we're adding some data. So that's just some malicious perturbation that we're going to be adding. And this, what we're adding is going to be very small, right? And it's going to be so small that, for example, if we have an image, we're going to be adding some perturbation to it, and it's going to be so small that the resulting image to us might look the same, but to a neural network, it will look very different because this perturbation that we're adding is going to add up. And that's what's going to make our example an adversarial example.
In simple terms, adversarial examples are often called the optical illusions for computers. And, we can see this in a more visual and mathematical way. So how is this created in a linear fashion? The most common method is called the fast sine gradient method, where you take an input, where you take any input. In this example, like I said, we're going to just use an image for like simplicity purposes. We have X. Now, what we do is you take the loss function of the ML model, and what you do is you take its derivative with respect to the input x. And after this, what you do is you apply a sine function, and you scale it by a very small factor, epsilon, and you just add it to the original input. And once you add, for the image, for example, if you add this, this fast sine gradient, gradient to each pixel, what you get is noise and a perturbed image over here, which looks like a panda, but to the ML model, it will misclassify it as a game.
Yeah, and it's very important to note that what we're adding here isn't just random noise, right? What we're trying to do is we're trying to add exactly the wrong values that we need to make the biggest difference for the neural network, right? And so if we're able to figure that out and it's not just noise, then we're able to add such a small amount that our image stays the same, but we're able to achieve a really big difference, right? So if we go back one slide, if you remember the eta, we're adding the eta, that's what this is.
So, we've looked at the math, we've looked at what adversarial examples are from very harmless standpoint, but these can have very serious implications in society and the world around us. Just to take a few examples, self-driving cars, facial recognition systems, verification, manufacturing lines, and hospital and medical scans. So, we gave you harmless images of puppies and cats and pandas, but this doesn't become funny when you consider life or death situations, such as distinguishing cancerous and non-cancerous medical scans, for example.
Yeah, and if you look at this image that we have of the stop sign, this is actually an experiment that was done where researchers were trying to fool self-driving systems. And what they actually found was that if you put tape in specific spots of a stop sign, they're actually able to make it so that the self-driving system doesn't recognize the stop sign. And so just to expand on one of the examples, for example, an early warning system, right? If we're able to create the exact wrong adversarial example, we can have false positives in some of these systems, right? So even with a cancer detecting system, we can have a false positive or a false negative when it's not supposed to be there.
So at the end of the day, it begs the question, how can we as humans trust these decisions made by ML models? How do we know what we're classifying is true? How can we trust these models?
Yeah, and just one more thing right before we move on, I wanted to sort of explain this picture here. These researchers, they're wearing these glasses, and these glasses are perturbation, right? These glasses are colored in the perfect way possible to completely fool the neural network. And so the neural network is not able to recognize these faces correctly. Yeah, so let's explain the solution a little bit more, right? And so remember we were talking about this eta that we're going to be adding. So now this is how we can actually train our model to take into account the adversarial examples that might come up and to make it a little bit more resistant to this.
So before going into the more effective solution, you also have to note that training the model with adversarial and normal examples until we decrease the error over time is a common solution, yet it is not effective and it's just inefficient to say the very least. That's where regularization comes in using the fast gradient sign method, which we mentioned earlier.
Yeah, sure. And so just to make a little bit of sense of this jumble that's here, basically this is our cost function, or this is our new cost function that we're going to be using. This was our original cost function, and what we're going to be doing is we're going to be taking a weighted sum. And so what's going to happen here is this is what we would normally train with, and this is what our model is now going to take into account. And this is some perturbation that's going to be added to make sure that our model can take this into account in the cost function. And so that when it's given some sort of noise like this, it knows how to handle it.
So yeah, basically just expanding a little bit more on the math, it might not be that important, but just to explain further, this new cost function, J tilde, basically what it's doing is like Zaid explained, it's a weighted sum, where in this case, we just take into account X plus eta, where eta is basically the fast gradient sign method applied to the original cost function over here.
Yeah, and just one last thing, if you note, this is the gradient with respect to the input.
right? And so we're taking into account what would happen if you change the input a little bit like this way or that way.
So, with regularization, we come to the results that researchers, at least in our paper, were able to reduce the error rate from 0.94% without adversarial training to 0.84% with adversarial training on the max out network model in particular.
And just to sort of explain the significance of this 0.94% figure, this was when the model wasn't given any adversarial examples. Like the researchers weren't trying to trick the model. But after they conducted this training, they still tried to trick the model. But even though they were giving adversarial examples, they still got a 0.84% accuracy.
So now that we've explained the problem, a potential solution that is being used, what's the big takeaway from all this and from the paper which we reviewed? Basically, we understand that the risks associated with machine learning, basically security is important. Being proactive in improving security is a must. An accurate model is not always a perfect model. And at the end of the day, despite all our advances in the field of ML and AI, as demonstrated by all these wonderful projects earlier, we are still in a very infant stage of this field. We have a lot of room for development, and the future is bright.
Yeah, and so what we want you guys to take away is that when we're using these models, it's very important to think about security, think about what can go wrong. And at the end of the day, there's always room for improvement. Thank you.
Questions?
Okay.
Yeah, thank you.
Okay, so I'm just curious, how easy or hard is it for an attacker to generate these attacks on models? Like, does an attack on like a faster RCN work on a YOLO V3? And like, how intimate of a knowledge does an attacker need of the model being attacked in order for an attack to be effective?
Yeah, I mean, while this wasn't really like mentioned or covered as extensively in the research paper, I would assume that causing a perturbation, like a successful perturbation to like efficiently like fool the model again and again over time, would require some like higher level knowledge of the model itself and how to like fool the architecture behind. But to give you like a solid, confident answer, I wouldn't say like I would be able to give you one at this point in time.
Yeah, what you're getting at is like black box tags, white box tags, right? And well, it does have some efficacy if you don't know the true architecture. It does.
If you know the architecture perfectly, you can compute, you can optimize for the most, for the input that will fool the architecture the most. Essentially, neural networks are linear models, so they can be actually encoded like a linear program that you can optimize. So you can optimize these epsilon inputs that you're going to give it so that you get the wrong answer.
Okay.
But if the architecture is very big, like fast RCNN, then these become very, very big optimization problems. So they're not solvable anyway. So then sampling with evolutionary algorithms before then also.
Thank you.
Thank you.
Are there any potential positive effects of like these adversarial attacks? Like, could it help, I don't know, maybe like eliminate bias or create more like fair machine learning model?
Okay, yeah, I mean, as shown as shown earlier, right? We saw that basically when we would train, I'm gonna apply this slide. I'm gonna apply math major, so I'd like to explain math.
By the way, do you guys mean 0.94, 94%, or really 0.94?
0.90.
That's like 1%.
Yeah.
That's tiny. That's not a big difference.
But yeah, going back to this, I think the positive in this whole thing is exposing all these, shortcomings of like multiple ML models used so extensively today. And like solutions like regularization, kind of what they do is help, come over these issues one by one. So like previously where we would just be using the original cost function to train the model. Now that we know that, problems like adversarial examples could be thrown at it in the future, we now train it with like, a renovated cost function based on, mathematical research, extensive like testing. And now what we know is that this new updated cost function takes into account the adversarial examples. So, I mean, I don't see like positive impacts as in like good for everyone, but I do see it as like a step of advancement in the field of ML. In like just general, you know?
Yeah, and then just to add on to that with like a specific example. So if we go to the stop sign here, right? This would be considered an adversarial example. And if we're able to take this into account, we can make sure our model sort of more understands the problem at hand, right? So when it's looking at a stop sign, it's not just looking for an S that's in that shape, right? Because if you cover up that S in an adversarial example, then the model can't perform anymore, right? And so what we learn is that if we're able to train with these adversarial examples, we're able to get a better picture of what we're actually trying to classify.
So are adversarial examples also just like, in the case of like images, just image skews, like covering up parts of the image and stuff like that? Is that still considered an adversarial attack then?
I mean, yeah, in this case, it would be like more of like a human created adversarial example, right? But the whole idea of adversarial examples is that like, to put it into like a big picture, it's something that we can tell is there, but like the neural network might not be able to, right? And so like in this case, it's literally covering up like an S or something. But like, as we showed like with the panda, right? We can't really tell the difference, but it's there, right? And so it's always like, it's a very broad definition, but it can be like human created, or it can be like computed like this too.
Expanding on what Zed said, based on the research we reviewed and like, you know, just other general articles which we studied and read, I feel like adversarial examples at the core are more like not just humanly altered, they're more altered to fool the network architecture itself. And so it might appear to be like, you know, an altering to the human eye, or like, you know, not, or it might even appear to be the same thing, but like deep down, like it could be an image or it could be any other example input. What it's doing internally is basically fooling the network, you know, the neural network or any other ML models architecture itself, so that in the way, like we said, in this case, you know, we're basically changing the input pixel like one input at a time to kind of accumulate over time, so that as a neural network kind of like trains and learns, is it really training and learning anything?
One more question, sorry. Can you go back to the stop sign? I'm just curious. Do you guys know, like, did the effectiveness of the attack vary depending on the angle in which the stop sign was viewed, and like lighting conditions and weather conditions and things like that? Was it pretty uniformly effective? No matter what.
Yeah, so this actual specific example wasn't part of our paper, but like I actually read into this a little bit, and from what I read, you know, it was a car that was driving towards the stop sign, and while it was driving towards the stop sign, at no point did it ever notice the stop sign. So it was a pretty effective example. All right, any other questions?
Can you explain the difference between what you said was the costly method of using training it with adversarial and normal examples versus regularization again? Because from the way I understand it, doesn't the regularization method just account for the adversarial examples in it? So what's the difference between like how computationally expensive it is?
Sure. Yeah. Definitely. That's a great question. So when we're training with adversarial examples, just think about creating a lot of different examples and just adding that to your input and training with that. So we can have like a lot of examples already pre-made, right? But when we're using this method, we're sort of giving it the worst case scenario from what I understand. So we're saying at each point, if we were to change it in the worst way possible and give it some adversarial example, can you still figure out what you're supposed to, right?
And yeah, I mean, in this case, what regularization is doing is it, like, you know, focuses and prioritizes on using the best possible updated cost function given an adversarial example based on the fast gradient sign method. When we say we're training the model with adversarial and normal examples, it's exactly what Zed described. You know, you're just training on a sample set of like a bunch of different images and adversarial like examples as well.
All right, thank you guys.
Hello, everyone. My name is John.
I'm Madhu.
And we'll be presenting the seminal paper AlphaGo, Solving the Humanities' Oldest Knowledge Base.
To start off with a little background on what actually is Go. So Go is an ancient, highly abstract, strategy-based board game. And in this particular board game, basic objective, to put it very simply, is just to enclose the maximum area possible with your rocks. So at first glance, this might look pretty similar to say like chess or checkers or other board games of that caliber. But there's actually a really big difference. And that difference is that AI has been able to successfully play and win chess, checkers, all of that. But up till the research leading up to this paper, it has not been able to successfully do that for Go. And this comes down to what we call search space to quantitatively like define the complexity of things. So search space is basically B raised to the D, where B is the breadth of possible moves and depth is the game length. So when you raise B to the D, you get the search space. And in this particular case for Go, the search space is 250 to the 150 possible searches. So clearly that is a really big amount. It's greater than the number of atoms in the universe, and it's definitely greater than the search space for chess. So seeing all of that, we can see that this massive search space makes a brute force approach impractical and also impossible. So that is why we go into the deep learning approach in this paper. So reinforcement learning for Go, just to quickly define some key terms in the context of this paper. So starting off with the state is a 3D volume with 13 handcrafted Go features. So those features include things like stone color ones, as you can see, zeros, like there's a whole list over there of features. And the 19 by 19 refers to the dimensions of the board. So it's just 19 by 19. And then the action itself is just the next move. So what is the next move that's going to be taken? And the reward is simply getting closer to winning the game. So as per reinforcement learning, we know that there's a state, there's an action, and we want to associate that through a reinforcer. So either a punishment or reward. And in our case, we chose, or not we did, but the researchers chose a reward. And that reward was again simply getting closer to winning the game.
All right, so now we'll look at the overall structure of how these networks are trained. So there are largely two big networks, policy network and the value network. So we'll begin with the policy network. So the goal of this network is to predict the next human expert's move. So the data that's given to the network is a lot of human experts playing each other on the internet or somewhere else. And then it's basically a classification problem to detect the state that the board is given and then output the next possible move that the expert could make. So here's the output. It's a probability distribution over the entire board. So the biggest volume given that state is the next probable move. And there are two approaches. Like one is supervised learning, where you learn from human data, as I just said. And then the second approach is the reinforcement learning, where you learn from simulated SL networks, the supervised learning networks, instead of human data. And the value network generally is like to predict the value of the states. So given like the state again, you're trying to predict how likely the next state will win the game. So here again, the highest point over there, the network is telling you that if you go to that state, you'll likely win the game. So we'll dive deeper into the supervised learning policy network. So goal again here is to maximize the prediction accuracy of the human moves using this. Oh, sorry, it's yours.
It's fine, but sure, whatever. So yeah, the supervised learning policy network, the first part of our training pipeline. So the goal, as he was on, is to maximize the prediction accuracy of guessing whether an expert human player would make that particular move or not. So the input given is a randomly sampled state action pair. And as per the fundamentals of supervised learning, we have a labeled data set, and that data set in this case is just prior moves and prior state action pairs made by expert human players. So the output given is the probability of that specific move being made by a human player.
The method that is used here is gradient descent. So it's an iterative algorithm used to maximize a probability function. So unlike gradient descent, where you're minimizing the loss function, here you're just maximizing the rewards. You're maximizing the probability function by continuously updating the dates or the weights, as you can see in the equation over there. And the final result for this was a 57% accuracy, and that was actually quite a significant jump from the previous state of the art of a 44.4%.
Okay, so we'll now use the reinforcement learning method. The goal here is basically the same, but we just want to make this better. So the input is different now. We generate like a pool of pre-trained supervised learning policy networks, and we just basically make them play each other in a simulated environment. So the method we use is a self-play with policy gradient. And policy gradient is this equation where you're given a set of weights and then you know the outcome of the game, which is this Z term. So depending on the result of the game, you're trying to optimize the weights so that if you win the game, you're trying to do more of those actions. And if you lose, you're trying to do less of those actions. The result is actually pretty good. So you win 80% of the games against SL policy network that Madhu just explained. And this is already good because it already beat state-of-the-art code prediction models. And another metric is that it wins 85% of the games against Pachi, which uses the Monte Carlo search program, which is supposed to be really good, but we do this without even search. And now we'll talk about the value network. So again, we're looking at the prediction of the outcome of the game. So the input of this network is the position of the games from the self-play data sets. So all the RL policy network is given into the network. And now we're outputting the state outcome pair instead of the state action pair. So the Z is the outcome of the game. So again, we're looking at the board and we're trying to predict for each state of the board how likely you're going to win the game. And this is an even simpler method. You regress over the data set with the least squared error or mean square error. And the policy gradient is very similar to what we just discussed before, but instead we take the difference between the prediction value and the actual result of the game.
Okay, so revisiting the network training pipeline, we just went over those two over there, the policy network and the value network. And we saw that even just using those two without the integration of a further search algorithm, we did see relatively successful results, which were higher than previous state of the art. So that was good. But this research went a step further and improved upon that by also introducing a search algorithm, a tree search to be specific. And that was kind of the crux of the paper and what made it different from previous. So this tree search kind of mimicked what a human expert player would be thinking and strategizing with a lot of complexity in advance. So in this case, the tree search would be trying to solve that problem of, oh, can we look ahead and predict what the next move is going to be? And based on those things, can we influence the current move that's being made? So yeah, this is what we're going to go into in the next few slides.
Okay, so this is basically the crux of the paper again. So it's called a Monte Carlo tree search. And this is actually a conventional method for like Go programs to use. But what makes this different is that we're using a customized policy and value networks that we use using deep learning approach instead of the conventional approach. So we're trying to simulate the entire game using a tree. So there could be a good analogy using like the parallel universe from Loki. So given like a state, you could take different actions and those actions will lead to like you being a firefighter or like a tenure professor teaching AI. So again, you choose some actions and then you result in a win or a loss. So some terminologies, action values Q and the bonus term U represents the famous reinforcement learning dilemma of exploitation versus exploration. And this means as you interact with the environment or as you play the game, when do you know that when are you confident enough that you know the value of a certain state? So you'll have to explore around first before making that judgment. And some more terminologies, the root node is the top one where you begin with. The edge value is the connection part, which is the action, and that's represented by Q plus U. And the leaf node is the very bottom, and you do a rollout. That's called, if you're at the leaf node and you don't have any child nodes anymore, then you do a rollout, trying to project into the end of the game so you know if you lost or won. And lastly, it is important to look at the subtree. So this one action value represents the entire value of the subtree. So this way you can truncate the depth of the search. So you don't have to go all the way down to look if this is worth or not. You can just tell by looking at this value. Okay, so the first two steps are selection and expansion. So actually the very first step is to initialize the policy networks, right? So we use the supervised learning approach instead of the reinforcement learning approach here. And you might ask why. Like we just told you that RL policy is better than SL. And the DeepMind team actually said that these initializations should be like random. And supervised learning learns from human data, and humans tend to play a diverse set of strategies, whereas RL tries to optimize a single set of strategy. So in terms of initialization perspective, I think you tend to like have more global minima if you're initializing with human strategies over a general set. So the selection works by selecting the action with maximum action value. And here you see the A equals argument max and the Q plus U. The Q plus U is again the action value. And the one before, the one I just talked about is the polynomial upper confidence boundaries PUCT algorithm, which is also widely used. And the important key insight here is to just know that Q is an action value that tells you how valuable this subtree is. So how much worth exploring this path is for you. The U bonus term tells you how much was the subtree explored. So how much have you already looked at this path before so that you're confident or not. So we can look at this equation for the U. It is actually inversely correlated with N, which is the number of visits you had for that segment. So as you visit a lot more times, you can have a decrease in U. But in the beginning, you never visited that subtree. So U will be big, and then you'll have a larger action value, which makes you want to pursue that route more in the beginning. Hopefully that made sense. And the expansion is very, very simple. So you traverse down the tree, you play the game, and then you end up at a leaf node where you don't have any child nodes anymore. And you just basically generate more children with the SL policy network so that you can continue searching.
Okay, so evaluation and backup are the third and fourth stages of our tree search respectively. So starting off with evaluation, it has two very distinct aspects to it. So the first part is where the state is passed through the value to determine its accuracy. And second of all, the fastest rollout policy network is used to play the game and then obtain a Q value that is updated. So after that, you move on to the backup, which is basically just back propagation here. So first, it traverses backward from the leaf to the root, so backwards. And the edges and action values are updated to reflect the mean of the evaluation. So this allows this to be like updated before the next simulation is run. Additionally, the evaluation starts off on a leaf node where the visit count is 0. So a quick recap and the results. So to start off, we mentioned the value of policy functions. And in the second or third slide, I mentioned that the main issue here, like the motivation behind this project, was because the search space of the game Go was just so large, it was just so massive that it wouldn't be like computationally efficient or even possible to approach it using a brute force method. And so because of that, we can easily see that just using a pure tree search method without the value function or policy function would not have been feasible nor efficient. So that's why we incorporated those two. So looking a little specifically into how that works and why it allows us to reduce the scale of computation, you can see first of all that the value function truncates the depth of the subtree by predicting the value of the state. So the value just being, whether you're going to win or lose based on that particular state, as well as that of the following subtree. And this truncates the depth of the subtree. So again, you don't have to like go through each one. Like once you see that a value is below the general standard of what you need in order to like maximize your chances of winning, you can stop and no longer go into that subtree, saving you the time and power. So moving on to the policy function, this truncates the breadth of the subtree by predicting the most likely action of the opponent. So if you know that an opponent is likely to take an action with a much higher probability than another, you can skip looking into that particular subtree and looking at the consequential decisions of it, but rather you can just look at what you think is going to be the most likely outcome, like what you think your opponent is going to use most likely in the next move. So yeah, based on that, we got our final result that AlphaGo reached a 99.8% winning rate. So obviously that is a huge jump from without the tree search, like with just the value function. So clearly, again, big jump. Also, it's important to note that this won against other programs like previously state-of-the-art programs, not just that, but also human players as well. So
you can see a picture of that guy looking pretty sad over there. He's actually the champion of this game, Lee Sedol, and in a pretty famous documentary, they actually saw the game, this AlphaGo algorithm beat him in his record. So again, pretty significant results here.
Yeah, just to do some free marketing, like I shed some tears watching this documentary. So I really, yeah, watch it. So takeaways, okay. The reinforcement learning, I think this paper really, brought into attention that RL is very, very powerful. And the basic gist is that you ask the right question and provide a reward function so that the agent traverses the environment by itself. You can not only depend on the human data set like supervised learning, but you can actually transcend human knowledge by having the machines play each other. And this leads to the concept of AI creativity. And AlphaGo played this 37th mood in one of the games. And it was actually, it calculated so that it was 1 out of 10K probability that a human will play this. So obviously humans, like, we never think that move will be relevant or never play it. But AlphaGo played it anyways. And then this led to the AlphaGo winning that game actually. So I think there's some more knowledge to be discovered outside of the human scope. And this is what I'm most excited about, the implications on scientific discovery. So the DeepMind team actually decided to build something called AlphaFold, which predicts the protein folding structure, and it tells you the function of that protein. And it works so well so that they decided to very recently launch a whole startup out of this lab, out of this technology called Isomorphic Labs, just for drug discovery. So I think it is very exciting. And there's a lot to look forward to. So thank you. Questions?
Who is the 99.8 win rate against? Is it just humans or humans and programs?
I believe the stat of 99.8 was actually a combination of all of main big state-of-the-art programs before that. So yeah, mostly other programs.
Do you guys know what lost it was?
No. We played 500 games and then they lost one.
No. Also, I don't necessarily know if AlphaFold is related to AlphaGo, but
Great job.
Right, thank you.
Yes. All right, hey guys. Today we're doing a presentation on new technology of you only live once, which is an image or object detection technology. And my name is Fred. David? Yeah. So what is you only live once? Well, it's a new object detection algorithm, which is based on using only a single regression as its network. And as the name says, I'm just only going to look once at where the objects are and what the object is. And this regression model is really fast. It's able to process images in real time at 45 frames per second. That means it can process video as well. Compared to more state-of-the-art technologies, it's not going to be as accurate, but it's going to be less likely to predict false positives. So it's not going to pick up some sort of object out of nowhere. And the thing that it struggles with is precisely localizing where an object may be. So we're going to take a look at some of the older technologies from before. So in the old object detection algorithms, they would go through an image
pixel by pixel and use classifiers for an object. And based on the pixels that they take, they're gonna decide if it is the object or not. And we have sort of a new DPM, which is it builds on the old models, and it actually uses a sliding window to look through the whole image. And these algorithms are really slow because you have to take the time to slide through the whole image and see where objects are before you're able to classify everything. And so here's just an example of what the older algorithms do. They kind of slide windows through and take, like, this is the bound for the dog, and this is maybe bound for another dog or a human right here. And that's really slow because they have to figure out the bounds, and they have to figure out if it is an object or not. And what YOLO tries to do is it tries to do everything in one swoop. So it's going to find where the image or where the objects are, as well as what the objects are. And you can see right here, it's able to detect person, dog, and horse.
Okay, so the way the model works is that it's a simple regression problem, and it takes an input as an image, as an S by S grid, and then predicts the bounding boxes, confidence for these boxes, and class probabilities for the image. So the output is an S by S by B times phi plus C tensor. And the phi comes from the bounding boxes, which consist of 5 predictions, X and Y, which are the coordinates in relation to the grid box of the boundary, width and height, which are the coordinates of the boundary in relation to the entire image, and the confidence level of the boundary. So this fancy diagram that they gave us is how they defined the model. It uses 24 convolutional layers and 2 fully connected layers. And the convolution layers reduce the dimensionality of the image, while the fully connected layers provide the classification and coordinates for the boundaries.
And for training, they use most of the convolution layers in the pre-training, and training was a week long. And after the week finished, the model achieved an accuracy of 88%. And then in detection, they use the last 4 layers along with 2 fully connected layers. And the reason they use both is because in pre-trained models, when you have both these layers, it's more efficient and it produces the more accurate outputs. And they increase the input resolution by a factor of 2 because the detection stage needs highly detailed images. And for the final layer, its function was to predict the class and bounding box probabilities. And they normalize the bounding box to values between 0 and 1 based on the overall image. They use a linear activation function for the final layer and leaky range for the others. For optimization, they use the sum squared error. And the pros of this, it's easy to optimize and it's simple, but the cons are they weigh all errors the same. For example, they weigh classification and localization errors the same, and this may not be ideal, along with the con of loss of gradient. So in an image, you have a lot of boxes that don't have any objects, and this causes the confidence intervals to be pushed towards 0, and it decreases the gradient that comes from the boxes that do have images. So both of these cons lead to divergence very early on. So the solutions they implemented in the loss function was creating lambda variables to increase the loss from object-containing grid cells and decrease the loss from non-object-containing grid cells. And I have the specifics there if you're interested. And then they also found the square root of the width and height of the bounding box probabilities rather than directly just finding the width and height. And this ensured that there was a difference between large and small bounding boxes. And then finally, they created a J variable for predictor specialization. So during training, they wanted to ensure that only one predictor was specialized for one object. And then just zooming out a bit, in training overall, they had this initial very low training rate or learning rate, sorry, because if it's too high at first, the model diverges. And then to address overfitting, they had a dropout layer of 0.5 to prevent co-adaptation. And what that means is it's a behavior that arises when there's codependency between each layer. And then they also heavily augment the data. And what that means is the original is at the top, and then they created different copies, slightly editing the size, saturation.
So in order to further understand how YOLO compares to existing models of object detection in real time, look at a table that the authors of this paper provided. This table shows that YOLO has the highest precision as compared to other existing real-time detectors such as DPM. And also fast YOLO, which is a faster implementation of YOLO, has the fastest FPS, has the highest FPS as compared to DPM. And in addition to that, YOLO also makes much fewer background mistakes than fast RCNN, which means that we can combine YOLO and fast RCNN to use YOLO to eliminate the errors that fast RCNN made. So what that means is we basically run both object detection algorithm in parallel, and then we cross-check the bounding boxes that they predict, and then we give a boost to the bounding boxes which both algorithms predict together. And that, as you can see, gives a significant boost in the accuracy. Another application of YOLO is in artworks. These three columns represent three different data sets of artworks, which YOLO was trained on and compared to other existing object detection models. And as you can see, the average precision is much higher than all of them. YOLO can be used because how fast it is in real-time detection scenarios. YOLO can be used in applications such as traffic managing, as you can see on the left. Although this is an image, but in reality, it is a YouTube video. So it is a live video and that's working. And as you can see that it can detect these cars, people, and even a person who is like kind of obstructed by a car. And there are also a clump of people over there, and it's able to detect that. Another feature of YOLO is that it generalizes pretty well to new domains, which means that if you train the model correctly, then it can basically generalize to anything you want. For example, here, we're not detecting traditional objects. Instead, what we're doing is we're detecting number and suits on the card. And as you can see how it works, it even works when the images are a little bit blurry. And also, this is also a YouTube video, so it is in real time. However, there are some limitations that YOLO face. For example, it struggles when there's a high density of object in close proximity. That is a problem that Fred mentioned earlier about localizing objects. For example, here you can see the bounding boxes are not perfect, to say the least, and this is because that YOLO only predicts a limited amount of bounding boxes per cell. So when it partitions the image into a cell and there is like, let's say 100 objects in the cell, it will only predict 2 bounding boxes, or like a specific number of bounding boxes which you set before you run the model. And another thing is that it doesn't generalize to object in new or unusual aspect ratios. And that means that when you train the model, let's say you give it a picture of a car, and then when you try to like let the model classify the car, but instead you rotated the car sideways, then the model, it's really hard for the model to like still perform consistently. So it has to like have seen the same thing before in order for it to detect it. And the same thing happens when you, let's say you zoom in on the car or you zoom in on a dog. And we have more example on that on the next slide. And the last thing here is that for each bounding boxes, it has the error is same. So that means in a big bounding box, in a large bounding box, an error will have a small weight as opposed because the bounding box is large. However, the same error in a smaller bounding box will have a large weight because the bounding box is small. And here are some example of
what I mentioned earlier, generalizing objects in different aspect ratios. Here's a bird identified correctly, but you see when the picture zoom out or the bird is like viewed at different angles, it's identified as a dog sports ball. And lastly, the conclusion. So YOLO distinguishes itself from existing models by eliminating complex pipelines, so for example, other models will take multiple scans through the image, or they will have different sets of neural networks to do different things. But YOLO combines them all together and views the problem as a regression problem. Furthermore, it can be trained on full images. You can give it a full image with multiple objects in it, and you just throw it in there, and it will be able to train. Lastly, it generalizes well to a new domain when you train it properly. So that means it is ideal for application, for many applications, such as taking arts or just taking playing cards. And given that it's fast and real-time detection scenarios, you can use it in situations where it requires fast and robust object detection. That's the original paper. You guys have
So how do you determine how many cells to partition the image into? I'm figuring out that I feel like, is that like a hyperparameter that that is determined when you're training on the data set, or how does it work?
Yeah, so when you train the model, you need to give it a value S for it to partition the image into how many cells you want. And that basically will depend on how you will let's say what object you're working with. For example, if you have a lot of small objects in the image and you want to distinguish every single one of them, in order to better localize the object, you will have to divide the image into smaller cells. If you have larger object, in this case, let's say there was nothing, it was only some bytes of this size, then you can get away with 4 boxes, right? Because it's very large and it's covering most of the boxes. But what you don't want is you don't want a lot of objects in the same cell, because then you'll have difficulty localizing.
So would you also say that you want the objects that you're looking for to be close to the same size, so that your cell size can be your cell size fits all of them, basically?
They don't have to be exact, because what happens is when, let's say YOLO makes a prediction here, the size of the bounding box can go beyond the size of the cell. So the size of the bounding box can go like this. But the trick is that for every cell that's covering the dog, it will make a prediction of the bounding. It will make a bounding box prediction. And then let's say a lot of time they made a similar prediction, then there will be, when you do the non-max suppression, then they will have a higher confidence.
I know some people have to go, we're already a little long, but we want to get a group picture real quick before our last presentation. Everyone like that. How would you like us to pose?
Such a good friend. Such a good friend.
One picture, we can do multiple rows. I should go on the front.
Be surprised. I just want us to get final.
Can you fit everyone?
Everyone in?
Yeah. You want to join them?
I thought it's only number.
Come in.
It just whoever's left.
Hey, smile through your masks. 1, 2, 3. Oh, can you move it? 1, 2, 3. Yeah. 1, 2, 3. Thank you. One, two, three. All right.
Right now.
I go for
Last presentation.
Yeah.
We would work it.
I love to know.
Okay, everybody, there's one more presentation. So we can all take our seats and let them present. You can all get out of here as soon as possible.
All right, hi everyone, good evening. Today we will be presenting Attention is All You Need. And my name's Karina.
And I'm Lorena.
I'm Ryan. Leo.
All right, and so first I have a small task for you all. So it's gonna be really simple, but just carefully try to read the words that will be on the next slide. Everyone done? Good? Okay, so even though you've probably seen the slide yesterday, you probably read at least some part of it wrong, right? And this kind of shows how we as humans interpret text. So instead of reading things sequentially in order, we kind of take in words and characters as a group and interpret it that way. And so on that note, let's talk about RNNs, or recurrent neural networks, which is generally the way that language is processed in AI, and why they actually aren't that great. So over here, we have a diagram and a picture, and it shows visually how an RNN works. So it kind of takes in inputs from before and uses that to predict the next word. So more technical terms, recurrent models such as RNNs or LSTMs generate a sequence of hidden states, h of t, as a function of the previous hidden states, h of t minus 1, as well as the input for position t. And contrary to how RNNs work, we actually don't process text in this way, right? As we've seen in the previous slide. So this kind of presents an issue. So the inherent sequential nature of RNNs precludes parallelization, which means we can't understand the nth word without first processing the first n-1 word. And this leads to a high computational cost. So the paper that we read presents a better approach, which is attention, and Lorena will be talking about that next.
Okay, so now let's look at attention. Why is it so great? So first of all, what is attention? So in this case, the transformer model basically looks at how much attention a word should look at to another word among the whole input sentence. So for instance, let's say we have this sentence as our input. Daniel didn't cross the street because he was too tired. So as human, we know that the word it should be referring to the word animal. So hopefully we want a model to find out that this relationship is the strongest. And this is exactly what transformer is doing. And then self-attention basically means that the word can pay attention to both itself and the rest of all the words. So how self-attention is used is that when the transformer is trying to encode or decode a word, it uses self-attention mechanism to let a word to look at rest of all the words regarding both position and the actual meaning of the word at the same time. So how exactly is attention calculated? So step one, we need to get the embeddings of all the words, which is to use vectors to encode and represent a word such that in the vector space, words that are similar to each other should be closer to each other. So as you can see, for instance, walked and walking, they have similar meanings, but they just like have different tense. So they are closer to each other in vector space, and which is important, and you'll see why. So step 2, we'll then find the query key value matrices for each word, which are all produced by multiplying the word embeddings that we got previously with the weight matrices we trained. So in order to, just to clarify, the query would just be the input word that we're currently trying to encode or decode. And the key matrix would just be used by the transformer to uniquely identify a word. And lastly, the value matrix would just be a way to represent the actual meaning of the word. And then step 3, we will be performing a dot product between the query matrix of the word that we're currently looking at with the key matrices of all the words in the input sentence. So why the transformer uses dot product? And now we can recall the word embeddings. So as we said previously, words that are closer in vector space are expected to have similar meanings. So you can imagine that words that are related with each other should have similar embeddings, or they should have similar directions, meaning that the data value will be small, so that we will have larger dot product value. Therefore, the more related the words are, the higher the dot product value will be. And this is exactly how transformer mathematically find out how words are related with each other. And then the transformer will divide the dot product value with the rules of the dimensionality to kind of just reduce dot product value in order to avoid managing gradient problem when it is applying softmax later. And then lastly, we'll multiply this softmax value with the value matrix of the word. So finally, now we get our attention value. So you can see that on the most fundamental level, the transformer is just performing a bunch of matrix multiplications. And given that nowadays matrix multiplication is really, really fast, so the transformer is really speeding up this whole computation process. And now we currently only have one attention head. In other words, we only have one set of query key value matrices for a word. So this may cause a problem that the final results may be dominated by the actual word itself. So for instance, the word, although there's only 2 words in the sentence, but the word thinking may be paying most of its attention to itself. So in order to avoid this problem, the transformer model takes a step further and have multi-head attention. So instead of having only one set of weight matrices, we now have multiple sets of query key value weight matrices, which are all randomly initialized. So by doing so, the transformer is able to focus on different types of relationships between a word with the rest of all the words in the input sentence, so that at the end, the transformer is able to produce a more comprehensive embedding for the word by concatenating all the results from all these different projections from the input to the final output. So for instance, when the transformer is looking at the word it, one of the attention heads may be looking at may focus more on the relationship between the word it and animal, while another one may focus more on the relationship between it and tired. So given that all the matrices are randomly and independently initialized, we can just do all of these computations in parallel. So instead of relying on results from previous layers as we have for the recurrent neural network, now we can just have parallel computation, which further enhance the efficiency of this whole model. And now after we know what attention is, and now let's take a look at the overall structure of the transformer.
All right, so there are 3 important parts or key points of the structure of the transformer. So we have the encoder and decoder structure, as well as the use of shifted outputs And the final one is the use of positional encoding. And so first, I'll give a little bit of background on the encoder and decoder. So here we'll use language translation as an example. So the objective is to translate the French sentence "Le chat est noir" to "the cat is black." So as Lorena mentioned before, we can embed each word of "Le chat est noir" as a vector. And then our encoder uses this embedding to output a context vector, which is essentially stores the meaning of the word. And then next we have a decoder. And so first there's a simple decoder, which uses input tokens as well as hidden states to predict the next English word. We can also have a more complex attention decoder, which calculates a set of attention weights that Lorena mentioned before. And this allows the decoder to focus on specific parts of the encoder outputs so that its next output is more accurate.
Okay, so just diving into the actual structure of the transformer, you're going to have the encoders and decoders, both of which have 6 layers. For each encoder layer, you're going to have 2 sublayers, a feed-forward network, as well as the multi-head attention layer that Lorena described earlier. For the decoder, you're just going to have 1 extra layer, which is going to multi-head attention layer that's going to take the inputs in from the encoder. Quickly highlights just some important parts about the transformer that I think you guys should know. First thing is that the output embedding is shifted right by 1 just to simply make sure that the model only makes predictions off of preceding information. And then lastly, we use positional encoding because we process the information in parallel. And because of that, we lose the information about order. And by adding positional encoding, we can retain that information.
All right, so here are the results of our paper. So it essentially scored a new state-of-the-art BLEU, which basically tells you how well a language is translated to another language. And it also has a runtime that is about 100 to 1,000 times faster than previous runtimes that we've seen before. So we can see that the transformer really has revolutionized the way that we approach language processing.
Just expanding a bit on how the transformer has changed our approach to NLP. Google also, in addition to the idea of a transformer, created BERT, which is its model for natural language processing, and is trained on the Wikipedia database. And what we see is that it's amazing at transfer learning. So you can train BERT on 11 different NLP tasks, and it outperforms state-of-the-art models on each of those tasks, even though it wasn't specifically designed for the tasks that we tested it on. So clearly transformers are very powerful and give BERT a sort of innate, or you could say it's almost like an innate understanding of natural language. And it sort of really enhanced our approach to NLP. And similarly, another application is Codex, which is part of GitHub's new Copilot feature. And it transforms natural language into code, as you can see in the image. So thank you so much. Any questions?
That was our last presentation. Thank you all for coming and staying. Grab some food on the way out if there's anything left. You're officially done with curriculum. There are curriculum people here. Hope you had a good semester. And yeah, that's all.
I'm trying to improve my thinking stuff. Where is
Do you want the
It's so funny. When the choreography, it's like, there's one guy who's and the choreo is basically him, and then we just dance on the side. Looks no, it's